Star properties from spectra. We cannot do experiments on stars in the laboratory. All we have to work on is the electromagnetic radiation we receive from them. We can, however, work out a lot about a star from this radiation. Apparent magnitude. The most obvious difference between stars is that some appear brighter than others. A bright star might emit a huge amount of energy per second, its luminosity, or it might be quite a low luminosity but be relatively close to us. How bright a star appears is called its apparent magnitude, and depends on how bright the star actually is, what's called its absolute magnitude, and how far away from us it is. In a similar way, car headlamps appear to get brighter as the car approaches. Their apparent magnitude is how bright they look to you. The absolute magnitude, which is unchanging, is how bright the lamp actually is. Early astronomers placed stars on a scale from 1 to 6, depending on their apparent magnitude or brightness. The brightest stars they gave magnitude 1, and the dimmest visible with the naked eye, magnitude 6. Magnitude 1 stars are 100 times brighter than magnitude 6 stars, meaning 100 times the amount of light would be received on Earth from a magnitude 1 star than a magnitude 6 star. A decrease in magnitude of 1, say from 1 to 2 or 4 to 5, means a drop in brightness of a factor of 2.51, as 2.51 to the power 5 gives a change of 100. So 5 drops of a factor of 2.51 gives us a change of brightness of 100. Absolute magnitude, how bright the star actually is, rather than how bright it appears from here on Earth, is clearly far more important to us than the apparent magnitude. Absolute magnitude is calculated from how stars would look if they were 32.6 light years away from us, to give a fair comparison from one star to another. Luminosity. This is the total power of the star, or the energy emitted by the star every second, and depends on the power per square meter and the surface area of the star. So a large cool star with a low power output per square meter, but a lot of square meters of surface area, could emit more power and be more luminous than a smaller but higher temperature star. Temperature. As well as having different levels of brightness, early astronomers noticed slightly different colours of the stars. This is due to their temperature. Just like a piece of hot metal will glow in different colours as its temperature rises, going from dull red through orange to yellow and white and so on as it gets hotter and hotter. Astronomers gave classifications of the stars, unusual letters of O, B, A, F, G, K and M. Other classes have since appeared, but these are the main ones. The classifications going down here represent a drop in temperature. So an O star could be between 30,000 and 60,000 Kelvin, for instance. This would give it a blue colour. A B star would be a lower temperature and would be a bluey white. An A star from 7,500 to 10,000 kelvins and a white colour. An F star has this temperature range and would be a yellowish white. A G star between 5 and 6,000 Kelvin would have a yellow colour, like our Sun. A K star from 3,500 to 5,000 Kelvin, orange in colour. And the coolest of the stars, from just 2 to 3,500 Kelvin, would be red in colour. A mnemonic for remembering this order of letters is O, be a fine girl, or guy, delete as appropriate, kiss me. Temperature. As well as having different levels of brightness, early astronomers noticed slightly different colours of stars. This is due to their temperature, just like a piece of hot metal will glow in different colours as its temperature rises, starting off dull red, then becoming bright red, and then orange, and so on. The astronomers gave these stars classifications with the letters O, B, A, F, G, K, and M, and as you'll see, temperature falls as we go through those classifications. There have since been other classes of stars, but these are still the main ones. An O-class star would have a temperature between about 30 and 60,000 Kelvin. It would be blue in colour, and the absorption lines would be caused by ionized helium in its outer atmosphere. A B-class star would be between about 10 and 30,000 Kelvin, bluey white in colour, and the absorption lines would be caused by helium atoms and hydrogen in the outer atmosphere. An A-class star between 7,500 and 10,000 Kelvin would be white in colour, and the absorption lines due to hydrogen and ionized calcium. An F star between 6 and 7,500 Kelvin, yellowish white in colour, with ionized calcium and metal atoms causing the absorption lines. A G-class star between about 5 and 6,000 Kelvin would be yellow, and would have absorption lines caused by calcium atoms and metal ions. Our Sun is a G-class star. A K-class star, a temperature between about 3,500 and 5,000 Kelvin, would be orange in colour, the absorption lines caused by metal atoms. And an M-class star, between 2 and 3,500 Kelvin, would be red in colour, and has absorption lines caused by molecules of titanium oxide, which, being molecules, produced a band spectra. A common way of remembering the order of the stars is this mnemonic: "Oh, be a fine girl or guy, delete as appropriate, kiss me."